To determine the volt-ampere output of an electric furnace when the voltage supply changes, you need to follow a two-step calculation process. The formula you will use is volt-amperes equals volts times amps. Firstly, calculate the current at the original voltage. In this case, the furnace is rated at 10,000 volt-amperes at 240 volts. To find the current, divide the volt-amperes by the voltage. So current equals volt-amperes divided by voltage. This gives you a current of 10,000 volt-amperes divided by 240 volts, which equals 41.67 amps. Secondly, calculate the volt-ampere output at the new voltage, which is 208 volts. Use the same current value you calculated in the previous step, which is 41.67 amps. Multiply the new voltage by this current to find the new volt-ampere output. Therefore, volt-ampere output equals voltage times current. This is 208 volts multiplied by 41.67 amps, which equals 6,900 volt-amperes. Thus, the volt-ampere output of the furnace when fed by a 208 volt system is 6,900 volt-amperes. The volt-ampere rating, often abbreviated as VA, is a measure of apparent power in an alternating current circuit. It's the product of the root mean square voltage and the root mean square current. Unlike watts, which measure real power, volt-amperes account for both real power and reactive power. Reactive power is the power that oscillates between the source and the load without doing any actual work. This is typically due to inductive or capacitive components in the circuit. In a purely resistive circuit, the volt-amperes and watts are equal. However, in circuits with inductive or capacitive loads, the volt-amperes will be higher than the watts. This difference is quantified by the power factor, which is the ratio of real power watts to apparent power volt-amperes. A power factor of 1 indicates a purely resistive load, while a power factor less than 1 indicates a reactive load. When dealing with electrical equipment, it's crucial to consider the volt-ampere rating because it represents the total load the equipment places on the power source. This is especially important when sizing generators, transformers, and circuit breakers. These components must be able to handle the apparent power demand, not just the real power. In the context of the electric furnace, the 10,000 volt-ampere rating at 240 volts indicates the furnace's apparent power consumption under those conditions. When the furnace is connected to a 208 volt system, the current remains the same, but the voltage decreases. This results in a lower volt-ampere output, as demonstrated in the calculation. It's essential to understand this relationship because it affects the furnace's heating capacity. A lower volt-ampere output means the furnace will produce less heat. This is something to consider when replacing a furnace or connecting it to a different voltage system. Understanding these concepts is useful for electrical engineers, technicians, and anyone working with electrical equipment. It helps to ensure that equipment is operated safely and efficiently and to avoid overloading the electrical system. It also helps in troubleshooting electrical problems and selecting the right components for a given application. Keep in mind that electrical calculations should always be performed by qualified personnel who are familiar with applicable codes and standards. These codes and standards are put in place to make sure that electrical systems are safe and reliable.